hear you. I hear sounds, but I can't make out words.
Yeah, I hope everybody can mute themselves except for the chair and the speaker, of course.
Yeah, that would be better.
Please start.
So, welcome to the APRG seminar, that is Analysis and Probability Group seminar. And it's my pleasure to introduce the speaker today, Professor Charles Fefferman from Princeton University. Actually, he needs no introduction. So he's going to talk about interpolation of data by smooth functions. Over to Professor Fefferman.
So, thank you. It's a pleasure to be able to speak in this seminar. It's one of the very few advantages of the strange times we live in, that so many meetings are held virtually. I'm going to be presenting this talk by using slides which I have shamelessly adapted which I have shamelessly simply copied from a talk that I gave in simpler times. So okay. I'll just follow along the slides. Okay, so these lectures, well, this lecture, there aren't going to be follow-up lectures in this seminar. These lectures discuss two closely related problems, interpolation and extension. Next slide, please. Oh, yes. Okay, so interpolation is the problem shown on the slide. If you're given a function defined on a finite set in Rn, the problem is to compute a more or less smoothest possible extension of the function little f to a function capital F defined on all of Rn. That's interpolation. Next slide. Okay, extension is a similar problem, but now we have a function little f defined on an infinite set E, a possibly infinite set, probably infinite. And the question is simply, does there exist a smooth function on the whole Rn that agrees with little f? Next slide. Okay, so in this first and only lecture, I'm going to state the theorems and unfortunately say little or nothing about the proofs. Subsequent lectures, which are not going to happen, will explain some of the proofs. Okay. Next slide, please. Okay, so let's get started. Next slide. Okay, let me start with notation and definitions. Next slide. Okay, there we go. Okay, so X is going to be our favorite Banach space of continuous functions on Rn. In this talk, X might be Cm, the m times differentiable functions, or Cm alpha, the m times differentiable functions whose mth derivatives are Holder alpha, or maybe Wmp, the Sobolev space on Rn. And an important point of notation, when you see a constant denoted by the letter C, then it always means that constant depends only on the choice of the function space X, which we're going to use to define what we mean by a smooth function. So for example, if X is the Sobolev space Wmp of Rn, then whenever you see a constant denoted by the letter C, it always depends only on little m, little n, and p, the parameters that define the space X. Okay, next slide, please.
Yeah, it has changed.
Oh, okay, so all right, now suppose that E is a finite subset of Rn. I'm going to use X of E to denote the space of all functions little f defined on E. Well, all right, so that's a simple thing, but we're going to put an interesting norm on it. And the norm that we put on a function little f in X of E is the inf of the norms in our Banach space X of all possible extensions of little f, as it says on the slide. Now it says inf rather than minimum. In elementary examples, the inf is not attained, so it really is an inf and not a minimum. And that, among other things, motivates the next definition. So suppose that little f is a function on E, and capital F is an extension of it that belongs to the space capital X. And let's say that A is a constant. Notice A is not C, so it's just any constant. All right, F is called an A optimal extension of little f if, first of all, it is an extension, so capital F agrees with little f on the set E, and furthermore, the norm in capital X is within a factor A of the least possible. And by least possible, I have to mean inf, not minimum. So that's an A optimal extension, and we're going to be interested in finding A optimal extensions for not so big A. Okay, next slide, please. So our problems, roughly stated, are as follows. Given X, E, and F, first of all, compute the order of magnitude of the norm of little f in X of E. How small can we take the norm of an extension? And compute a C optimal extension of F, where C is one of these constants that depends only on F. Now, that's a vague statement of the problem.
Sir, this
I'm
capital norm of this capital F X E. What is XC, sir? Can you just repeat this? What is this XC?
Oh, this C, remember, C is just some constant that depends only on the space X.
Yeah.
Okay, so a C optimal extension means that the norm, we have to compute a capital F that agrees with little f on E, and whose norm in X differs from the inf of all possible such norms by at most a factor C, where C is some constant that depends only on the space X.
At this norm of F, capital F X, is it finite?
Oh, yes, and it has to be finite. Yes.
Why?
I mean, that's part of the definition. So it's not, I mean, I have not solved the problem. I've stated the problem. The problem is to find a capital F that does.
Are you including that this norm of, this is part of definition, but your definition doesn't say that actually. Can you go back to the definition a little bit?
Oh, so capital F is required to belong to the space X for this. Okay.
X. Okay. In that thing.
Okay. But by the way, thank you for the question. Please, if anybody has any question, please just speak up. Okay. Okay. So, all right. So those are the questions. Now the questions are okay. The questions are not very precisely stated. We don't know what order of magnitude means. We don't know what it means to compute a function, and so I'm going to explain what it means in the next couple of slides. Okay. So to compute the order of magnitude of the norm of f in X of E means that we're going to compute using a computer some number, which I'm going to call the triple norm, as you see on the slide, the triple norm. So that's simply some number that we can compute from little f in such a way that we are guaranteed that it differs from the thing we are really interested in, namely the norm of little f in the space X of E, by at most a constant factor as on the slide. Okay, so that's what it means to compute the order of magnitude. Now, how about computing a function? I have in mind using a computer, but a function is inherently an infinite object and a computer is inherently a finite object. So what do I mean by computing a function? And the next few slides explain. Okay, so let's say we're computing a function in Cm of Rn. Here's what we mean by computing the function. Okay, next slide, please.
Yeah, I have changed.
Okay. All right. So we sit at a computer terminal. We enter the data. The data means the set E and the function little f. So we type all that in. The computer then performs one-time work. Maybe it types on the screen, please sit patiently while I work. And the computer executes an algorithm which is called the one-time work. And then it displays on the screen, thank you for your patience. I finished with my one-time work. I understand how to extend the function, and I welcome your queries. You may then query the computer, and the computer will respond to your queries. A query consists of a point X in Rn. So you query the computer by typing in the coordinates of X, and in reply, the computer executes a query algorithm and outputs not only the function, but all its derivatives up to order m at the point X. And that's all we can reasonably expect because our function capital F is supposed to belong to the space Cm. So that's the information to which we're entitled at the point X. Okay, onward. Okay, so that's what it means to compute a function for purposes of this talk. Next slide, please. Okay.
Yeah.
A technical point. I want to make sure that the response to a query X depends only on the data that we entered and on the point X and not on anything else. So for instance, if we ask successively 20 queries to the computer, I don't want the answer to the 20th query to depend on the 19 previous queries. That's the content of this slide. Okay, next slide, please. Okay, now, all right, there are algorithms and algorithms. We want efficient algorithms that make minimal use of the computer resources. And so, all right, what computer resources are we talking about? Next slide, please. Thank you. There's the next slide. Great. For computation of a function in CM, the relevant resources are, first of all, the number of computer operations to do the one-time work. By a computer operation, I mean, for example, multiplying two numbers together. The number of computer operations required to answer a query, and the size of the RAM. Let's say one memory cell in the RAM can store, let's say, one real number. Normally, when you try to optimize three things, there are trade-offs, but in this case, we're lucky we're going to be able to optimize all three of these things. Let's see what standard we should hold ourselves to. So let's look for trivial lower bounds for the work. So suppose that the number of points of E is capital N. Then the one-time work is greater than or equal to capital N because we had better read the problem. Okay. The query work is greater than or equal to 1 because we had better, let's say, output an answer. Also, it would be nice to read the problem. The memory that we need is at least capital N because we had better store the problem. Okay, so those are trivial lower bounds. For the purposes of computing the order of magnitude of the norm of F, the relevant computer resources are simply the number of computer operations we have to perform and the size of the RAM. And then we're simply outputting one number. Okay, so those are the trivial lower bounds, and we're going to get remarkably close to those trivial lower bounds. Okay, next slide, please. Next slide, please.
This one or the next one?
Let's see. The next one after that. There we go. Yes. Okay. Now, a fundamental point that I have to make before going on is that I'm only interested in algorithms that always work, regardless of where you put the points of E. If you make favorable geometric assumptions on the geometry of the set E, for example, if E were a lattice or anything like a lattice, this problem would be much, much easier. Okay, so I want algorithms that always work. And so in the next few slides, I'm going to show you a few delicate cases. But before we do, let me just pause and ask, are the statements of all the problems clear? Is the notation clear and the questions? Are there any questions regarding the questions?
I have one question.
Okay.
You said that you have to optimize this thing in these three things. What does that mean actually? Optimize this query and
you mean to optimize, let's say, the number of operations and so on? It means, is that the question?
Yes.
Okay, so what it means is I'm going to show you an algorithm. Well, I'm going to claim that there is an algorithm. It's complicated, so I won't show it to you in detail. There is an algorithm. I'll tell you how well it performs, and I'm going to assert that no other algorithm that does that task can do better. Okay, that's what I mean. Okay.
These three tasks you are optimizing.
Yes.
But is there any mathematical formulation for that? What is the meaning of that?
I mean, I will. Well, the closest I can come is that I will make claims about a particular algorithm, and then I will assert that there is strong evidence that no other algorithm could do better. But in order to say that precisely, of course, you need to specify the model of computation, and I have not done that. So really, I guess this is just an emotional statement about what I believe, rather than a precise mathematical statement. But the statement of what the algorithm does is precise. The statement that it cannot be improved is emotional. Okay?
Okay.
Okay. All right. So the claim is.
May I ask a quick question?
Oh, yes, please.
I was
Yes.
wondering if I understood correctly. So this is about the order of magnitude of the x sub e norm of f. And you gave a definition. This involves identifying a number triple bar of f. So
Yes.
do I understand correctly that in general, of course, we don't know what the middle term is. We don't know what the x sub e norm of f
Exactly.
is. So what you are saying is that one has a proof that delivers a number which says that even if we don't know the size of the middle term, we have this inequality, that this number is comparable to the desired norm. Did I understand correctly?
Yes, absolutely. You understood perfectly.
Right. So in principle, we will never know what the middle term is, but we have a good enough idea, right?
Exactly. Okay.
All right. Thank you very much.
Oh, sure. Thank you again. I'm glad to take questions. Any other questions? Okay. So now let's look at some examples in which the problem is delicate. So remember, if E looks anything like a lattice, then the problem becomes much easier. So here are a few examples in which the problem is somewhat delicate. So in the first example, our space X is, let's say, C5 functions on the plane. There's nothing magical about the number 5. And I took the plane because I can make pictures of it. Now, I'm not going to tell you what the function little f is, but I'm going to tell you what the set E is on which little f is defined. It's the set of red dots in the picture. The salient feature about the red dots is that all but one of them lie extremely close to the horizontal axis, but just one of them, which I have denoted by X, is noticeably off the axis, a lot more than the others. And so then the question is, at the point Z, what is the derivative of our capital F, the extension of the function little f? What is its derivative in the vertical direction? Okay, and the trouble is that if it were not for the point X, there would be basically no information. All of your information comes from the red dots, which lie essentially on the horizontal axis. You have ample information on the horizontal derivative and no information on the vertical derivative. The point X allows you to say something about the vertical derivative because you can compare, you can make a difference quotient using the points X and Y. That the displacement vector from X to Y is transverse to the horizontal axis, and therefore you have some information which then you can transport to Z. However, so there is enough information here to say something about what the vertical derivative is at Z. However, it comes from the point X, which need not be one of the 100 points closest to Z. So if you have any algorithm that tries to understand what the Taylor polynomial is at Z based on the 100 closest points to Z in the set E, you're guaranteed to fail. So information can come from far away and you'd better detect it. All right, let's look at the second example. Okay, in the second example, again, so please move the slide up. I have a feeling there's a delay of a second or two, but okay, there we go, perfect. Yeah, probably because of the speed of light. Okay, okay. So in example 2, X is again C5 of R2, and E is again the set of green dots, but now, red dots, sorry, but instead of lying close to the x-axis, they lie close to this funny curve gamma, which is the zero set of some polynomial of low degree. In particular, the degree of the polynomial Q is less than the number 5 in C5 of R2. And that has basically the same issue as before, except that instead of a horizontal axis, you have this funny curve. But now remember, in the statement of the problem, no one gives you the funny curve. You are just given a set of red dots. Your algorithm had better realize that the curve gamma is sitting around and respond to it. So our algorithm is going to have to detect this phenomenon and respond to it real fast. Okay, next slide. And in the final delicate example I'd like to show you, the space X is now C5 of R3, and E is going to be the set of dots in this picture. And now our red dots lie, all, or perhaps all but a few, lie incredibly close to an algebraic surface, the zero set of a low degree polynomial. But they also lie quite close, not as close as to the surface sigma, but also quite close to a curve gamma. And in that case, the problem is influenced by both sigma and gamma, but you are told neither sigma nor gamma initially. You had better become aware of them and respond to them. And you were given only the red dots. Okay, and so next slide, please. So the moral of those three examples is that we had better decide quickly whether E lies close to the zero set of a polynomial of low degree, and if such polynomials exist, we had better respond to them quickly, because we want our algorithm to take not too many operations. Okay, next slide, please. Next slide, please. Thanks. And so real algebraic geometry enters the story. Okay. Okay. So I think I have motivated and explained the problem. Here are the first results for CM. So this is a result with my wonderful, very smart Israeli past collaborator, and I hope future collaborator, Boaz Klartag. And so the theorem is as follows. So our Banach space X is going to be CM of Rn. E is a finite subset of Rn. Let's say the number of points of E is capital N. Okay, and we're given a function little f on E. Given all that, we can compute a C optimal extension capital F in the sense that I described before, using, and now here are the computer resources. At most, Cn log n operations of one-time work, C log n operations to answer a query, and Cn memory cells of RAM. So again, this n is the number of points of the set E. All right, so that is a precise mathematical statement. And furthermore, we can compute the order of magnitude of the norm of little f in the space X, X of E, sorry, using, okay, and here are the computer resources. At most Cn log n operations of work, and at most Cn memory. Okay, now, so those are the statements. Now, very likely these upper bounds are best possible. In particular, notice how close they are to the trivial lower bounds. They differ by from the trivial lower bounds that I mentioned before only by log factors. Furthermore, you can give much easier versions of the problems that I posed today. You can give much easier versions of the problem for which it's far from obvious that you can remove the log n factors. So in a theoretical sense, these are, I mean, first of all, these algorithms work. The computer resources used are as in the theorem, and it is very likely, although I certainly do not claim to have a proof, that they are best possible, and so that would mean this problem is completely solved. However, unfortunately, they are of no practical use because some of the constants capital C that depend only on the space capital X are nevertheless very big, at least as in the current versions of the proof. And I would actually be very interested to find improvements in the arguments or in the algorithms which mathematically do nothing, but which have the nevertheless which have the effect of greatly lowering these enormous constants C, because these are real practical problems, and the obstruction to these algorithms being real practical solutions is precisely these large constants C. Okay, now so far I think I have stayed sort of from 50,000 feet. I haven't said anything about how the algorithms work or how anything can be proven or any theorems. That's not so good for a math talk. let me try to say a little bit more. So these algorithms are very closely related to Whitney's extension problem. This is a problem posed by Whitney in 1934. So here is Whitney's question, and we're going to answer it later in the talk, time permitting. Okay, so Whitney's question is this: fix integers little m and little n. Now suppose that capital E is some subset, maybe infinite, maybe awful. Okay, so E is some subset of Rn, and we are given some real valued function phi on the set E. Whitney's question is, how can we decide how can we compute whether phi extends to a function in Cm of Rn for that fixed m? Okay. If such an extension capital F exists, we can ask further questions. We can ask, how small can we take its Cm norm? Can we take capital F to the extension to depend linearly on the function phi to be extended? And what, if anything, can we say about the derivatives of the extension at or near a point of E? Okay, that was Whitney's classical question. And in order to answer it, one has to take into account three big ideas. So I'd like to explain the three big ideas. Okay, so the first of the big ideas is the classical Whitney extension theorem, also posed in 1934. So now we're given a compact set E in Rn, and for each point of the compact set, we're given not merely a function value, but a polynomial of degree m. And the question is whether there exists a function in Cm whose Taylor polynomial at each point of the set E is equal to the prescribed polynomial that was given to us. That was Whitney's question. That turns out to be an easier version of Whitney's extension problem. And the answer is that if you look at the obvious necessary conditions that arise from Taylor's theorem, those are already sufficient. So of course, if you have a Cm function, its Taylor polynomials at two nearby points have to be close together in some quantitative sense. And essentially that condition is enough for the existence of the capital F. All right, so that was Whitney's theorem. Okay, the next lecture, which is not going to happen, will present the classical Whitney extension theorem. Okay, next slide, please. Okay, now, all right, so three big ideas regarding Whitney's extension problem. That Whitney's extension theorem was the first. The second big idea is the idea of a Glaser refinement. So Glaser was a French mathematician working in the 50s, and he solved Whitney's extension problem in the case of C1 of Rn, so one continuous derivative. And he did this using a geometric construction, which he called the iterated paratangent bundle. And that idea was further developed by Ed Bierstone, Pierre Millman, and Wiesław Pawlucki for Cm of Rn in the case when the subset E is subanalytic. Okay, and further development yet of that idea played a key role in the complete solution of the Whitney extension problem. And so we're going to see Glaser refinement later in the talk, time permitting. Okay.
What is the term mean? What is this term mean? Subanalytic?
I'm sorry, subanalytic. All right, very roughly speaking, not correctly. If a set is defined by finitely many equations and inequalities involving real analytic functions, then it is semi-analytic. And subanalytic is something like that, a little bit more general. Okay. Okay, so but the word subanalytic is unlikely to appear again in this talk. So okay. The third big idea, due to Yuri Brudny and Pavel Schwarzman, is the idea of finiteness principles. So I'd like to explain what those are. Okay, next slide, please. And in particular, the connection. Previous slide, please. The connection between Whitney's extension problem and the algorithmic question that I've been talking about before. that comes via finiteness principles. Okay, now to the next slide. Thanks. Okay, so what is a finiteness theorem? Well, here's the original Brudny-Schwarzman finiteness theorem. Well, they conjectured it and proved it in some cases. All right, so given m and n greater than or equal to 1, there exists an integer constant k and a real constant c that depend only on little m and little n, such that the following holds. Next slide, please. Okay, let's suppose we've got a function little f mapping e to r. Okay, so e is some finite subset of Rn. It's important that e should be finite. It can be arbitrarily big and very complicated, but it has to be finite. The theorem is wrong for infinite e. Okay, suppose that we take a 6-point subset. I'm sorry, not 6, a k-point subset, and we look only at the problem of extending the given function little f off of that subset S. Suppose that for every such S, we can find an extension whose norm is less than or equal to 1. Then you can solve the whole extension problem, the whole interpolation problem, with the norm at most E. So in order to figure out whether little f can be extended to a function with not so big norm, or whether inevitably any extension has an enormous norm, it's enough to look at every k-point subset for a fixed k. Okay, next slide, please. So that's a finiteness theorem. Okay, and this theorem and several related results were conjectured by Brudny and Schwarzman already in the 80s, although the proofs came much later. Okay, next slide, please.
Jalib, in the previous thing, finiteness thing, what you are concluding that is the not if.
So what I'm,
yeah.
I'm sorry, say again.
Yeah. What you are concluding actually?
Okay, what I'm concluding is that there exists an extension of the given function little f from the whole set E to all of Rn in such a way that we get a Cm norm at most a constant. Okay, so let's look at the simplest case. In the simplest case, let's say we're the simplest non-trivial case. Let's say I give you some enormous finite set E in the plane, and I give you a function on that finite set. Okay. Now I ask, I would like to find a function in C2 of the plane, and I would like to I would like to make its C2 norm as small as I can. Okay.
Then this notation should be capital F, I think.
Yes, the notation was for the capital F. So
but you have written small f.
That's because so remember that the norm of small f in the space Cm of a set is defined to be the inf of the norms of all possible extensions. Yes. So miracles happen. I believe it is actually correct as written. Okay, but is
just
it
an
clear?
interjection, sir. Can I ask?
Yeah.
Yeah. Does C depend upon K?
Does what depend on K?
Capital C.
Oh no, rather capital C and little k both depend only on little m and little n, both of them. So they are K and C are, so to speak, dependent variables, and the independent variables are the dimension of the Euclidean space in which we're working and how many derivatives we want.
Okay. Thank you.
Sure. Any other questions? Okay, let me give a little example. Maybe this is contained in the next slide. Let's see. I'm sorry, I don't remember what's in the next slide. Please, next slide after this one. Still next slide. Okay, here are variants that were actually proved. Okay, okay, next slide after this. Okay. Okay, I'm mentioning that the proof of some special cases. There we. All right. Let's look at the simplest case again. C2 of the plane. I give you a finite set and a function on the finite set. I ask you to extend with a C2 norm as small as I can manage. how can I get lower bound for the possible norm of an extension? Well, I can take out of my big finite set, I can take 6 points, and I can forget about everything else in the set E except those 6 points. And I can just look for functions that agree with little f on those 6 points. And then I can, I haven't explained how, but because there are only 6 points, you can actually compute approximately the least possible C2 norm of an extension. Well, okay, that's fine. And now for each 6 points, you get a lower bound. Okay, the claim is that the maximum of all of those lower bounds is approximately an upper bound. That's the content of the finiteness theorem. So that's great because it's something you can compute. There is a weak spot because there are an awful lot of 6-point subsets of a given set E. And so, okay, on to the next slide. I'm going to tell you. I'm sorry?
Can you hear me?
Yes?
Yeah, the number of points you're choosing, the K. So is there any way of choosing? For example, if it is R2, if you choose the points from only line, suppose the points are lying on the line, then it won't be a good solution, right?
Well, all right. So if your points lie only on a line, then life is much simpler. And I guess for C2, what is it? 3 points are enough. In general,
no, if the points are lying, like I am only choosing from the K points from a line. Suppose all those points also lies on a line.
Oh, yes. Okay.
So in that case, our approximation won't be that good, right? Because we don't have any information on the other directions.
Oh, okay. Well, all right. So if our points lie on a line, the way I have chosen to state the problem, I can, for instance, so let's say our line is the x-axis. I can declare that I'm only interested in functions of x, okay? And if I find a good interpolant that as the function of x, and then I declare that it also does not depend on y, that does not necessarily predict the function that I want, but this C2 norm of that interpolant as a function on the plane cannot be improved, right? That's so I am not saying that there is a unique solution to the problem, and precisely in the case you described, there is not a unique solution to the problem, but there are, in fact, but on the other hand, it is not the case that there is no solution to the problem. There is a solution. There are multiple solutions. Does that answer your question?
Okay.
Okay.
Yeah.
Okay. And any other questions? Okay, let's go on. All right, so onward. Next slide. All right, so I'm going to now state a refined finiteness theorem. So now again, we fix little m and little n, and their purpose is just little m is always the number of derivatives, and little n is the number of dimensions of space. And there are then the claim is that as before, there is a real constant c and an integer constant k that are determined by how many derivatives we're looking at and how. Right. So now, now suppose that we are given a finite subset of Rn, and let's say capital N is the number of points of that set. Okay. Notice I have not yet specified a function little f on E. I've just given you the set E. Well, in that case, from E, we can extract a list of little subsets called S1 through SL, such that, okay, let's see what these sets do. First of all, there are not too many of them. Remember that damn it, they're of the order of n to the 6th 6-point subsets. But now the number of sets in this list, S1 through SL, is at most a constant times n. The number, the n is the number of points of E. So the length of the list grows only linearly with the pardon me, with the size of the set E. And furthermore, each one of these sets, S sub L in the list, each one of these little sets has at most k elements. That's why I say that they're little. So instead of looking at all little subsets, as in the previous finiteness theorem, we're now only going to look at the subsets in the list. And now we bring in functions f, and we're going to see what this list does. So given a function little f on E, if you want to know the norm, its norm in Cm of E, remember that means the inf of the Cm norms of all possible extensions to functions on the whole Rn, that is comparable to the max of the corresponding norms in which you restrict f to the little subsets S sub L. Okay, so that means that once I give you the list of little subsets, that it becomes possible to compute the order of magnitude of the Cm norm. And those sets, all right, so once you know those sets, you are in good shape, at least for computation of the norm. And furthermore, the sets themselves can be computed from E. Okay, and the math behind the proof of that theorem. So that's actually a mathematical theorem rather than an algorithm, except for the last part where I say things can be computed efficiently. The existence of such subsets is a theorem, which you can state without worrying about computation. Now, I think for the first and only time in this lecture, I would like to give you a little glimmer of the proof. So I need a little more notation to do that. And so if I give you a function capital F now, which is a nice smooth function on the whole space Rn, I'm going to denote J sub x of f, J for jet. This is the M jet. Okay, Jx of f is simply the mth degree Taylor polynomial of f when expanded about x. And that belongs to the finite dimensional vector space script P of all such Taylor polynomials. Okay, so that's the notation Jx of f. Okay, and now we're going to ask a key question, which is, suppose that there exists a function capital F in Cm whose norm is less than or equal to capital M, some given bound, and that agrees with the data. So capital F is equal to little f on E. If that's true, then what can we say about the jet of f at a particular given point x? That's the key question. Okay, next slide, please. Okay, and so that motivates a definition. So given our function as usual little f defined on the set E, E is as usual a finite set, x is some point of Rn, and capital M is some positive number. Pardon me, I'm going to define the set gamma of xm, and it is going to be simply the set of all jets at x of functions capital F that agree with little f on E and have Cm norm at most capital M. That's the definition of gamma of xm. And so, of course, to ask what can you say about the jet means what can you say about this set gamma of xm? Well, let's make a couple of obvious observations. The first observation.
What is Jxm? I just forgot.
I'm sorry. So x. What is x?
Jxf.
Oh, Jx of f is the mth degree Taylor polynomial of f when expanded about x. So it's a polynomial.
Yes.
Okay.
Yes.
Isn't this somewhat reminiscent of the construction of the paratangent bundle for the case m equals 1?
You are extremely well informed and or very smart. Yes, absolutely. Yes. This whole, I mean, everything I'm telling you now does not come from out of the blue. It is built on lots of previous work, including that. Yes.
Thanks.
Sure. Okay. Any other questions or comments? Oh, okay. Let me stay with this slide for a moment. So there's this set gamma. Notice that what can we say immediately about gamma? Gamma is clearly convex because, for example, if I have two different ways of extending little f, let's say if I can extend it to capital F sub 1 and capital F sub 2, then I can take any convex combination, like let's say 1/2 F1 plus 1/2 F2. And that's still an interpolant, and its norm is still less than or equal to capital M. And its Taylor polynomial is therefore the average of the two. And so just because of that simple remark, the gamma is obviously convex. On the other hand, let's be careful, gamma might be empty, because maybe I've been greedy and I have picked my capital M so that there are no such interpolants. And then gamma is the empty set. So gamma is obviously convex, but beware, it might be empty. Okay, now remember before I said that we have to deal with some real algebraic geometry in order to come to grips with interpolation problems. And the real algebraic geometry is now encoded in the size and shape of these convex sets gamma of xm. In particular, okay, next slide, please. Okay, in particular, if capital E is close to the set where some polynomial is 0, okay, so that was a source of trouble before. You can see that because the set gamma of xm is very long in the direction p. P is a polynomial, therefore it is a vector in the space of all polynomials. It gives rise to a direction in the space of all polynomials, and the gamma is going to be very long in that direction. Okay, next slide, please.
This term, I am not able to understand. What do you mean by this long?
Long. Well, so we have a convex set in a vector space.
Yes.
So I haven't given you a precise definition, and you were right to question it. But in some sense, if you know, forget about the fact that this is the space script P. Just imagine you are in, I don't know, R3, and I show you some convex set in R3. Maybe it looks sort of like a ball. Maybe it looks sort of like a thin needle. Maybe it looks sort of like a pancake. If it looks like a thin needle, it is long in one direction. If it looks like a pancake, it is long in 2 directions. And if it looks like a ball, it is sort of long in 3 directions. But these are vague. These are vague statements. I have not made precise statements, and to do so, I would have to write down some inequalities, and it would take time, which I don't have.
Okay.
Is that yes?
Yes,
okay.
yes.
Okay. And any other questions? Any other comments? Okay. All right. So to prove the refined finiteness theorem that I told you about before, the thing to do is to first understand the approximate size and shape of these convex sets gamma of xm, and then to use that information to compute a capital F with controlled CM norm that agrees with little f on E. That if I had to give a 1-sentence or 2-sentence, whatever, summary of the proof, it would be that. When I say understand the approximate size and shape of gamma, what I really mean is guess the approximate size and shape, and then prove that the guess is right. And in doing so, you construct a capital F. Okay. And I'm afraid that's as much as I have a chance to say in this survey talk. Okay, so I want to say that these convex sets gamma and their close relatives sigma, which I haven't defined, will play a fundamental role in all our results. And what are all our results? Well, I don't have time to explain them. Maybe this is the moment to give a little commercial. I'm sorry, this is perhaps shameless. This lecture is actually so these slides come from lecture number 1 of a series of 10 lectures, which were then made into a book by Aryeh Israel and me, called something like Interpolation of Data by Smooth Functions. So if this subject interests you, the book is available. It's probably available online. Okay, end of commercial. Anyway, let me return to algorithms and give a little application. This is the application is to removing outliers. Okay, next slide, please. Okay, so now, as usual, suppose that we're given a function little f on the set E. E, as usual, is a finite subset of Rn, and we're going to look for a little subset S sitting inside E called the outliers, with the property that if you remove S from the set E and you try to interpolate, you can do so with a much smaller norm than if you were forced to include S. So the next slide, pardon me, the next slide shows a simple one-dimensional example. There's the simple one-dimensional example.
Sir, can you please repeat what you said?
I'm sorry, repeat? Okay.
Yeah, okay.
All right. So we're given as usual an interpolation problem. So we're given a function little f on a finite set E. Okay. E is in Rn. We're trying to extend little f to a function capital F in Cm with as small as possible a norm.
Yes.
But it may happen that there is a small subset, just a few points of E, which are the problem, in the sense that for the full E, you cannot, I mean, any extension necessarily has a very large norm. But if you change the problem by removing the few points of S from E, and if you then look at the subproblem, or the problem that arises if you erase the points of S, suddenly you can do much better and interpolate with a much smaller norm. And the question is that true? And if so, can you find the S? Is that clear?
It is clear.
Okay, good. Let's look at a simple one-dimensional example. Okay, so in the next slide, you'll see a simple one-dimensional example. So here I have I would like y to be a function of x. So this is a one-dimensional problem, and we're looking at a graph in R2 because you imagine that you were supposed to draw the graph of some unknown function. So my okay, in my interpolation problem, I want to draw a C2 function, let's say, or a C3 function whose graph passes through all the dots I've drawn, the black ones and the red, or the blue ones and the red ones. Okay, well, it's very clear. Look at the red dots. They are going to make this problem very difficult, and inevitably, any function whose graph passes through those points has a very large C3 norm. But if I remove the few red dots and look only at the blue or black dots, whatever they are, there is a perfectly tame, very nice function. You can draw it with a pencil. You can draw its graph with a pencil, and the C3 norm is not so big. And so removing those very few dots makes a big difference to the problem. Okay, and this is motivated by the idea of performing an experiment. Imagine that experimentalists give you a lot of data and you would like to guess some function based on the experiments, but every so often someone screwed up. For example, many years ago, in addition to being a math major, I was a physics major, and I was supposed to measure the mass of the proton, and it weighed something like 1/10 of a gram. So in averaging together what all the students got as their answers, my results should simply have been thrown out rather than averaged together. Okay, so in experimental work, one often throws out outliers, and this is motivated by that. Okay, let's state a theorem. Okay.
May I?
Yes.
In case of Lipschitz functions, can we choose this outlier set to be empty? Is that so?
Well, you can always choose the outlier set to be empty. The question is, if I tell you how many points you are allowed to remove, how much good will it do? So for example, if let's say, think of functions of one variable and think of functions defined on the set 1, 2, 3, 4, 5 through 10, okay? Now, suppose that my function is 0, except at the point 6. And at the point 6, the value of my function is 1,000. Okay. Well, I can make a Lipschitz extension of that to the whole line, but its Lipschitz constant is going to be big because I have to get from the point 5 to the point 6, and my function value has to go from 0 to 1,000 in one jump. Okay. Well, if I remove the point 6, all of a sudden my subproblem is look at functions defined on the sets 1, 2, 3, 4, 5, 7, 8, 9, 10, and my function is 0. And I want to interpolate that. I can do that with a marvelously small Lipschitz constant. Okay?
Okay.
Okay. Any other questions or comments?
Yeah, good.
See, I would like to ask, if you take little f to capital F, can this map be linear or affine or anything?
The map from little f to capital F? Yes.
Yes.
Yes. Yes.
Take different
Okay.
f and then let little f go to capital F. Can this map be linear, affine, additive, or anything like that?
Yes, yes, absolutely. It can be linear. Yes, I didn't state the theorem, but yes, one can take a capital F whose norm is as small as possible up to one of these constant factors C, and it depends linearly on little f. Yes, thank you for the question. Okay, and well, for a sketch of the proof, see the book in my commercial. Okay, and any other questions or comments? Okay, back to outliers. So the set capital E can be enumerated as x1 through xn in such a way that somehow x1 is the worst point, x2 is the second worst point, and so on, so that for any integer z less than or equal to n, if you look at the first z points and you call that sz, that is sort of the best possible set of z outliers to try to remove in the following sense. So here's the precise statement of what sz does. Take any s contained in E with at most z points. Okay, then, oh, I'm sorry, not at most z points, at most c times z points. C is a small constant depending only on the dimension and the number of derivatives. If you remove sz, then the resulting norm that you're able to achieve is less than or equal to what you could have achieved by removing s, but with a constant c. So this means that you can win an unfair competition against an omniscient opponent with against an omniscient opponent. So here is the contest. We pick a number z. Okay, let's say we're given 50 billion data points, and we're allowed to remove 1,000 of them. Okay, well, I can pick my 1,000 first points in the enumeration, and I am guaranteed that by removing my 1,000 points, my norm will be no more than, let's say, 10. Will be no more than 10 times the norm achievable by the omniscient opponent who however is only allowed to remove 100 points. So this competition is unfair in two ways. First of all, the number of points I am allowed to remove is a constant multiple of the number of points that the omniscient opponent can remove. And furthermore, my norm is allowed to be a constant factor bigger than the norm attainable by the omniscient opponent. But all right, so this competition is unfair, but nevertheless, this SZ is, I think, a reasonable candidate for the set of outliers to remove. And I mean, the omniscient opponent really has to be omniscient, because to pick actually the best Z very likely is an NP hard problem. So we relax it a bit. All right, now, all right. I see that it is 10 o'clock, and I propose to stop. So instead of some long list of further results and problems, this is a taste of the subject. And so I thank you for listening. I thank you for active participation. You have not simply sat back and said or thought nothing. You have asked insightful questions, and it's been a pleasure. Thank you.
Thank you very much for an interesting talk. So we have some time for questions.
So I have two questions.
Okay.
So when you are extending this F to say capital F, there are maybe many extensions, right?
Absolutely.
So why, how this linear business is coming? I am not getting that.
Oh, the claim is that out of the many possible extensions that do the job, it is possible to pick one that depends linearly on the data.
Okay, for each F, okay.
Okay, so that is, there exists. So if I fix the set E, fix this, we're working in CM of Rn, and I tell you what M and N are, and I fix the set E, but I don't tell you what little f is. I can produce a linear operator from functions on E to functions on Rn in such a way that if I am given any particular little f to find on E, and if I then take capital F to be the result of applying that linear operator to the little f, that does the job.
Sir,
And it will also be bounded, right?
I'm sorry? And the operator is bounded, yes.
the first thing, can you go back to where you have defined this capital F, sorry, F3, there is no, right? Okay, let me ask, I ask this question. You are really, first you are using a sort of computer science problem to optimize these three things, and you are posing and proving some result in this way, mathematical form where this, then I am not able to see the link actually. What is the
link between the algorithm and the theorem?
Yeah, mathematical theorem and the problem which you have motivated some.
Okay. You did not see it because I did not display it. What you do is you take you take the proof of the theorem, and you use that as the idea for building the algorithm. But in order to build the algorithm, you also need additional ideas. So again, you did not see the connection between the proof of the theorem and the algorithm. And if you had seen it, you would have been clairvoyant. I did not show it. I simply asserted that the proof of the mathematical theorem underlies the algorithm. But for example, I did not show you the algorithm and I did not show you the proof of the theorem.
Okay.
Okay.
And probably one last question.
Sure.
I have a question.
Oh, wait. Oh, okay. Somebody is.
Yeah, Munna, you can go ahead first.
Okay, so you said that long needle, that is clear that in one direction it is long.
Yes.
In pancake it is also somehow clear. This circle, why it is long in three direction?
Oh no, that depends. In which directions it is long depends on the particular problem that it comes from. So for example, suppose that I give you a lattice in Rn. So I take the unit square and I make a 10 in the plane, let's say, and I make a 10 by 10 lattice, okay, or 100 by 100 lattice. That's my set E, and I try to extend some given function from that lattice to the whole plane. So I asserted that that's essentially trivial. I didn't explain, but that is essentially trivial, and that's manifested in the fact that if you calculate this set gamma for that problem, you will find that it is a little tiny set. It is, so to speak, in let's pretend that we're in R3. It is like a P. It is a very small convex set. On the other hand, take, let's say, one of the take the first or the second of my three delicate examples, where I said that there is some curve in the plane which makes the problem difficult, and you have to notice that the curve is there and respond quickly and so on. That curve is the zero set of a polynomial, and that polynomial gives one direction, let's say in R3. And so then the convex, the gamma would look like a needle for that interpolation problem. And finally, if you look at the last of my three delicate examples, remember it was, that was many slides ago, unfortunately, but remember that there was the capital E lived in three-dimensional space, and it was very close to an algebraic hypersurface and somewhat close to an algebraic curve sitting in that hypersurface, so that there are two polynomials floating around, okay? And that means there are two directions, and then what that would mean about the gamma for that is that it's very big in one direction and big but not very big in a second direction and rather small in the third direction. So the size and shape of the gamma depend on the character of the interpolation problem. And the number of directions in which the gamma is big rather than small has a lot to do with how hard the interpolation problem is and with the strategy for solving it. So does this convex set look like a needle, a pancake, or a ball, or a pea? Okay, does that answer the question?
Yes, yes, yes. So,
Okay.
and in some practical purposes, there might be some situation where finding this E would be difficult or something.
Oh, all right. So in practical situations, so let me first make a disclaimer. I think I made it before, but it's important. Because these constants are so big, these algorithms, even though they are theoretically optimal, at least I believe very strongly that they are theoretically optimal, nevertheless, they are right now of no practical use because the damned constants C are too big. I would love to change that. And in fact, there is interesting work, current work, by Aryeh Israel and collaborators on precisely that. But we're nevertheless, they are very far from anything practical. Okay. Now you asked, all right, in practical problems, might it be difficult to identify the set E? I'm sure that in practical problems, everything is hard, including finding the set E. Okay. There was a conflict. Two people wanted to ask a question at the same time, and I'm afraid that the second person was just shut out. Who wanted to ask a question?
Yeah, there was.
It was me. Yeah, it was me. It's really not a question. So actually, I would like to understand more about what's being done, and if you have maybe lecture notes or survey articles there.
Oh, okay. Oh,
Yeah.
thank you very much for the question again. So let me repeat the commercial. So there, first of all, there is a set of, all right. So what you just saw today was about the first 1/3 or 1/4 of of a set of, I don't know, 100 and some slides. Okay. Now those slides form lecture 1 of a series of 10 lectures. Those 10 lectures were expanded into a book. The Luma has actually the Google Drive that points you to all to the slides from all 10 of the lectures, and there are perhaps I don't know, there are perhaps 1,000 of the slides altogether. That could be interpreted as being forbidding, but I tried to make the slides such that they are very easy to understand. So you know, there are, I mean, I did not strive to impress. I strove to explain. So there is that, and then those 1,000 slides were expanded into a book by Aryeh Israel and me. It is called something, I think the exact title is Interpolation of Data by Smooth Functions, or something like that. The authors are Aryeh Israel and me, and they at least they try very hard to explain very clearly, without jargon and without trying to create unnecessary difficulties, what is going on, what are the problems, what are the ideas, what are the results. So thank you very much for your interest, and if you want to explore further, maybe have a look at the slides and or the book. Okay.
So can I share the slides with the people interested in?
Oh, absolutely.
Okay. Yeah,
absolutely.
I can send you. Yeah.
Thank you.
I have a question.
Yeah, someone has a question.
Yeah, I am asking the question regarding the constant you were talking about. It's very large.
Yes.
If you fix the dimension of the space, and the space itself, Rn is fixed and Cm also fixed, is it related to? Is it how to decrease the constant? Is it related to choosing the points? Like.
Oh, okay.
Yeah.
Okay.
If the number of points of like lesser than the constant will be less, or you need to choose, for example, k points in such a way that with respect to some distribution, that the constant is less. Is that way we can decrease the constant?
Okay. Well, let me start by saying that because of I guess of defects in the internet, I heard an approximate version of what you said, but I didn't hear a precise version. So I'm afraid I'm going to have to guess what you asked and then answer the guess. Let me first state the guess. So maybe the quick way to say it is, I have said that the constant C is too big. What does the constant C actually depend on, and what do I mean when I say that the constant C is too big? And how does and how is that affected by, let's say, the choice of the particular problem that I am solving? So well, let me ask, did I get your question right?
Yes.
Okay. So well, so of course there have been, I mean, I've stated a lot of theorems and algorithms and whatnot, and so there are a lot of constants, but what many of them have in common is that for, let's say, if we are working in the space of functions, let's say with 4 derivatives of 3 variables, okay, my constants are allowed to depend on the parameters 4 and 3. When I say that the constants are big, I mean 2 different things. First of all, mathematically, as a, I mean, how, all right, these constants depend only on how many derivatives and how many dimensions. But how do they depend on how many derivatives and how many dimensions? And the answer is badly. So let's say worse than exponentially in the dimension, and worse than exponentially in the number of derivatives. That has been recently improved by the team of Aryeh Israel, let's see, Boaz Klartag, Abraham Fry Pearson, and Jacob Caruth. So I'm happy to give them credit. And so now maybe they depend merely exponentially on something or other. I have on my to-do list to learn their work, and I have not done so yet. So let me not screw it up. There's some progress on that, but one could ask a different question, namely, never mind the mathematical dependence. Suppose I'm interested in, let's say, C2 of R3 or C3 of R2. What values of these constants do I actually get? And the answer is, I have not worked it out. It's conceivable that that the constants are not so enormous in those cases, but I mean, the exact values of the constants will then be very implementation dependent. Here's a simple remark to illustrate how delicate the formulation of the question is. So suppose I want to define the C2 norm of a function. What is that? Well, so let's say I can take all derivatives of order up to 2, and I can take the soup of all of them in absolute value, and I can add them together. Or I can take their maximum. Or I can take the square root of the sum of the squares. All those norms are equivalent, but they are different. And if I want to know what the constant C is, I had better make a choice. So I think a reasonable thing to do is to pose the problem in the following way. You get to make your own choice of any reasonable C2 norm, which helps you in the task of making the constant C smaller. Okay, now tell me not a constant that depends only on blah, blah, blah. Tell me an actual number. C, C is 23, and tell me that the norm of your operator, or the constant C in whatever theorem, is 23. Okay, well, that's highly implementation dependent, but in principle, for small values of little m and little n, one could calculate it, and it's conceivable that it's not enormous, but no one has even calculated it. Is that an adequate answer?
Yes.
Another question.
Yeah.
So I was, yeah. Am I audible?
Yes.
Yes. Yeah.
I am curious about the guarantee that you had about the removal of outliers, and I was thinking about the kind of problem that would motivate this sort of a result. So let me state the wrong motivation, because initially I thought that is where it was leading, which was if the norm is very, very large, then what this is saying is that all the extensions are very, very choppy.
Yes.
Now, if one is looking at image recognition problems, the whole issue here is being able to deal with recognizing, say, edges.
Oh, yes.
Where necessarily the functions are very choppy, and and a large norm is good. It is capturing reality. So I was sort of curious about, so this could not be the motivation. So I was curious about what the motivation for the result on outliers comes from.
Okay. So the motivation. So I certainly agree. I mean, it's clear from what you say that that the motivation is not from trying to detect edges in images. Oh my God, no.
Right. I just draw a contrast. I mentioned that.
Right. So suppose that experimentalists are trying to determine some function. Let's say some physicists or chemists or engineers are trying to find a formula for pressure as a function of density and temperature, let's say. Now, of course, there are phase transitions, but let's say that we are in a region where we do not think there is a phase transition. And so a bunch of people perform a bunch of experiments. Okay. And then they get a bunch of data points and they are going to try. So in this case, we're trying to find a nice function of two variables and we think it is smooth. But whenever experimentalists do their work, inevitably something sometimes goes wrong. One day the machine doesn't work, or the student performing the experiment is incompetent. I have been that student once upon a time. Okay. Or for example, one is measuring some very small effect and a truck drives down the road and shakes the experimental apparatus. And so you have a massive data, and the data are mostly reliable, but every so often there is a data point that is complete garbage. And if you believe all the data, you are completely out of luck. So imagine, let's say the pressure is a function of temperature and density, and it is a nice smooth function, and you graph lots and lots of data points from experiments, and they all lie on this graph, but there are 5 data points that are completely off the graph, nowhere close. Okay. In terms of the temperature and the density, you can find points very close to the outliers where the data are correct. But then at the outliers, the dependent variable is just completely off. Will garbage. That motivates you to try to throw out garbage. You know, something went wrong in the experiment, and all the rest seem to indicate that the function is smooth. That's the motivation.
Right. Thank you.
Sure.
Another question. You were talking about the anisotropy of these sets gamma. Now, in the requirements for these algorithms you were talking about at some point of time, you said that one should have the ability to recognize points that are not in general position to be able to do so fast.
Yes.
So does the geometry of these sets gamma play a role in understanding that there is a bunch of data not in general position?
Yes, absolutely. Yes, that's. I mean, maybe it's a slight exaggeration to say that's the whole point, but that's a big part of the message. Yes.
All right. Thank you very much.
Sure. Thank you.
Yes, I have a question. So, am I audible?
Yes. Yes.
Yes. So you said that the number of these outlier sets, L, so that grows linearly.
Yes.
But you also said like K depends on M and N, but like do you have like, or is there any hope of getting a some sort of an upper bound on what K is. Like, because we want those sets, like the number of points to be small, right? I mean, so
Right,
is there a kind of,
Okay.
is there a sort of hope of getting any upper bound on what K can be?
Okay, that is, all right, thank you for the question. That is, I think, a crucial question. Okay, there are explicit upper bounds on K, but they're not very good. I mean, I said that in too weak a manner. They are very bad. Okay, but there are completely explicit upper bounds, but there is no reason to believe that they are optimal. Okay. Now, one could think that the way to do the algorithms is to use the theorem with a particular value of K, and once you have calculated the max on all of those K, then that's the answer. But in fact, the algorithm is merely motivated by the proof of the theorem. I mean, one could simply apply the theorem to get the algorithm for the calculation of the norm, but one can do better. So the question, so first of all, can one find an optimal K? Well, I think that's a hard problem, but there is hope. But I certainly don't, so I have an upper bound. It is not a good upper bound. There is the problem of finding the optimal K. All right, that's hard, but there's hope. But then one need not solve that in order to give reasonable performance for the algorithms. Even if the K, the best obtainable K, or the very best theoretically obtainable K that we will never know, even if that is very large, there is hope for making the algorithms perform a whole lot better. But there may be hope, but right now there are not algorithms that have reasonable performance guarantees.
Okay.
Is that a reasonable answer?
Yeah, sure. I was just,
okay.
Okay, thank you.
Sure.
Are there some more questions? Yes. Thank you very much once again. I think we have taken up a lot of your time. Thank you very much for agreeing to give a talk and then spending time with us. It was a very interesting talk. Yeah.
Oh, sure. I hope you enjoyed it.
Yes.
Thank
you. We did.
Thank you.
We should.
Let me stop.
Is there any way to really